Okay, it's been a while since we had a video, but we are now moving into section 4 and 5 of chapter 9, and we're looking at kind of this relationship of, so we were talking about polarity, we've talked about geometry, and now we're going to get into why the certain shapes, why the certain number of bonds, and it's related to those outer electrons. That's ultimately how and why things bond. So what we're going to get into is really where the s and the p orbitals, which is where those outer electrons exist, how they play into the forms of bonds that atoms have. So when you think of a covalent bond forming through the sharing of electrons by adjacent atoms, so our first example is hydrogen. Two hydrogens share electrons, and well, hydrogens have their one electron in their s subshell, and so the electrons are being shared, but those s electrons, or that one electron, is in the s subshell, so their s subshells are overlapping. Where when we think of another atom, like chlorine, which has its outer electrons in the p subshell, well, then the p electrons, or the one electron that is going to be shared with, like, let's say in hydrochloric acid, HCl, the electron would be shared uh, from the electron in the hydrogen would be in the 1s subshell, and it would overlap with the outer electron that's in the 3p subshell of the chlorine. And so this approach can only occur when orbitals on the two atoms overlap. So that's the only way you can have electron sharing, is if the orbitals overlap, meaning that the electrons are spending some time in the region near the other atom's nucleus. So when we think about this overlap in relation to bonding, there's a certain distance uh, that basically benefits the or favors stability. And so the nuclei of two atoms come close enough together to kind of hit this best distance where the attractive forces of the nuclei of atoms to the electrons of the opposite atoms is good compared to the repulsive force of the two nuclei from each other and the repulsive forces of the electrons from one another as well. So too close, and it takes too much energy for them to be together, and too far away, and less stability. And we can and that's basically the distance between the two nuclei when we talk about, radius or bond length, things like that. So we've got outer electrons exist in the s and the p subshells when we talk about our major bonding around around structures. But the thing is, when you think of the s, the p, and all the p orbitals, their shapes actually make it hard to imagine the tetrahedral, the trigonal, or even and the bipyramidal, and some of the other geometries that form. So what we need to do is think of, well, when these structures come together, how are they hybridized, or how are orbitals hybridized? Because technically you've got, so our example here is beryllium. Beryllium has 4 electrons total. 2 electrons in the 1s, 2 in the 2s. Now, the electrons in the 1s, those are core electrons. They are not going to do anything in the bonding for beryllium. And so it's really those 2 electrons that are in the 2s. Now, if the 2 electrons were simply in the 2s, you would think, well, why would beryllium want to bond with anything? Because those electrons are paired. And so we have to kind of explore, well, they must be occupying singly orbitals rather than be paired up, or else there would be less need for them to form. So in the ground electronic state, it would not be able to form bonds because it has no singly occupied orbital. So what actually happens, but if it absorbs a small amount of energy, that electron that's in the 2s uh, gets bumped into the 2p orbital, and therefore you have two electrons that are singly, and therefore would be looking to pair up with two other atoms to share electrons and to fill those two shells. So what happens, so if you think of the s orbital and the p orbital, so mixing the s and the p orbital yields two degenerate orbitals that are hybrids of the two orbitals together. So these sp hybrid orbitals have two lobes. So you take an s and a p and you hybridize them and you get the two sp orbitals. And they've got these lobes. One of the lobes is larger and more rounded, as is the s orbital. And so think of it as, so you've got those two sp hybrid orbitals sitting there, your atom's in the middle on the far right, and you have two lobe regions where that atom is going to share electrons to create two bonds. So that's why beryllium always forms two bonds. It has an sp hybridized orbital. And you always get this linear or 180-degree alignment. And this is what we observe in regards to the geometry for it. Now, keep in mind the halogens, which you may notice here, the halogens, they always form one bond because they only have one free electron in a p orbital. So you're always going to get this one orbital shape. It's not going to hybridize. With hybrid orbitals, the orbital diagram for beryllium would look like this. So rather than having like 1s, 2s, and 2p, with the 2p having three orbitals and the 2s having one orbital, the sp has two orbitals and the 2p has two orbitals instead, because one orbital has been pulled or been combined with the s orbital. So the sp orbital are higher in energy than the 1s orbital, but lower than the 2p orbital. So if we look at boron, boron has two electrons in the 2s and one electron in the 2p. With a little bit of energy, we can promote one of the electrons in the 2s into the 2p, and we get a sp2 hybridization where we have three orbitals with single electrons, and therefore you get it hybridized into three degenerate sp2 orbitals, which then creates three large lobes available for bonding, hybridized orbitals available for bonding, and thus we get a trigonal planar geometry out of it. Carbon has, oop, that kind of jumped ahead. Carbon has two electrons in the s and two in the p, and so by promoting with a little bit of energy, you get the 2s, the 2p, hybridize them all, and you get four electrons in the sp3 orbital, and thus get a tetrahedral shape. So having four hybridized lobes and giving a tetrahedral shape. Then expanding, once we get into the third energy level, there are some atoms that can expand into the 3D section, and this is where it allows us, and we've talked about in the past, and without really going into greater detail on why this is, why some atoms, why the larger atoms can form more than four bonds, like when we talk about like, yeah, but I thought the valence electrons needs to fill to 8. Well, so when we get into elements that are in the third energy level, they have a d subshell that electrons can be promoted into. So you can get a sp3d hybridization where you're basically promoting a single electron into the d subshell and getting a situation where you can have 5 bonds, okay? And then So an element that might do this would be like sulfur. So one of the reasons, actually, no, this would probably be more like phosphorus. So phosphorus has 1, 2, 3, 4, 5 electrons in its outer shell and the third shell. So it could promote one of those electrons into the D subshell, and you could get so phosphorus could potentially form 5 bonds, or arsenic is a good example of something that could do that. So this leads to this sp3d orbital shape and get into the trigonal pyramid, and then go a little bit further with this concept and promote. So when you have 6 electrons, like sulfur or selenium, in their outer shell, you can promote 2 electrons into the D subshell and get the sp3d 2 orbital and able to get to that octahedral shape. So this is why, or how we're able to get there, to get to those bonds, is this promotion of electrons into the D subshell, which then makes it possible to make more than 4 bonds, kind of, passing up the octet rule to create some larger, bonding relationships. So once you know the electron domain geometry, you immediately know the hybridization state of the atom. So if you know that it has 4 electron domains, then you know that the hybridization is an sp3 because it's got 4 domains where electrons exist. And we'll explore this a bit more in class. And that's where we're going to stop for now. And yeah, we'll see you in class tomorrow.